Okay, so we're just
right,
before you go into it, you're talking about taking a hammer. You're standing on the Empire State Building.
Let me start.
You throw a hammer out, or you throw or drop a hammer. Which one's going to hit the ground first?
Hold on, calm yourself. We need to start before that. So if we want to know the answer to this question, we have to understand vectors. Now, vectors are like this, okay? You take a vector. And if this is a vector, this represents velocity. This is an arrow, by the way. It's just representing velocity. We'll say this is like what?
Big.
5 meters. Well, okay, fine. Big enough?
Yes.
Good. All right. Vector. We'll say this is some random quantity. This is like 5 meters in this direction, right? But we don't really know, like basically, if this is a speed vector, we'll say this is velocity. It's 5 meters per second in this direction, okay? So what we can do with that is we can break it into its components. Very simple. This is like physics 101, but, So we break it into its components. Now, we call them components because they are very independent of one another, okay? Let's say that in, 2 seconds, right? It's going to reach a height of 10 meters because that's 5 meters a second, right? It doesn't matter if I increase this vector, which would, of course, change the angle of this vector to much lower. The vector's still going to hit 10 meters in 2 seconds. That's just a rule. If you break that up, you get what I'm saying, right? You're following me. Basically, even if I increase the horizontal velocity, it's not going to affect how high it gets or how fast it moves upward. Diagonally. No, not diagonally. Vertically. So we've got that down. Hold on. Let me get the eraser.
So this is the hammer, right? We're throwing
Alright, so if we have a hammer, right? And let's just imagine that we have a velocity vector, right? I was going to say acceleration, but that's not right. And so, basically, if I have Empire State Building, right? And I drop a hammer.
Right.
And I throw a hammer, right? Or you know what, better yet, let's just go with acceleration vectors, because that's better. So if I'm at the top of Empire State Building, let's just do that, and this is me up here. Hey. Yeah, okay, I'm not an artist. And we just have one hammer. And I'm not really going to draw like a good hammer. I'm going to do like a T, alright? And then I have one hammer. So I applied a force to this hammer, and I threw it that way, right? And we'll do the hammers over here just for the sake of showing you what the forces are acting on it. Now I threw the hammer that way, and if I wanted to do velocity vector, basically the point I would make is this one has a velocity vector going this way, sure, but its velocity vector is increasing at the same rate as this one's velocity vector, right?
Right.
Downward. Its components of velocity are the same downward. Same thing with acceleration. So if I were to write this out in acceleration vectors, well, this vector disappears here because it isn't accelerating. That's just a constant speed. So its acceleration vectors are the same, regardless. So even if I throw the hammer and I drop a hammer at the same time, they're both going to hit the ground at the same time because its downward vector components are going to, essentially, they are going to be the exact same. So they'll hit the ground at the same time.
Right.
Regardless.
Meaning
that
all right, I'm going to kind of dumb it down. Meaning that if you take a hammer and you throw it out at the same time as you just drop a hammer, both hammers will hit the ground at the same time.
Right. Now you think about this and you're like...
Only if you throw it out parallel.
Right. So you think about this and you think about it and you go, well, that's kind of interesting. But then let's apply this to something even cooler, right? If I shoot a gun... Okay. And I drop a bullet at the same time as I pull the trigger, both bullets will hit the ground at the same time. Which is kind of crazy, because you think, technically they wouldn't because of curvature of the Earth, but in the end, it's negligible, so they're really going to hit the ground at the same time. Now, we can apply this to things like why light bends in water, right? You might be thinking, how could that work, right? So, basically... we have air out here, right? I'm just gonna do a quick little dot thing.
Yeah, it's
So-
a whole bunch of dots for you guys. Can't
Air
see.
is not very dense. It's very spread out. You
Right.
can't. Light passes through this like crazy. Sure, it might hit like a molecule here and there, and then like have some trouble. But for the most part, visible light doesn't even interact with air. So we're getting the
Right.
we're getting the full thing here. But when you take water, water is much more dense.
So dots are closer.
Yeah, the dots are much closer together. You get it. Look, pixels are only so big, and there are only so many megabytes to go around. All right, so when light passes through this big, denser area, it has to slow down because you have it bumping into some molecules. Some of the light gets messed around. Some of infrared light might be absorbed and re-emitted as visible light, or not visible light. Maybe like ultraviolet, for example, right? Okay, so we know that. Well, that means that light slows down. If you actually measure the speed of light in air versus a vacuum, the light will actually move slower, and it's the same thing for water. If you measure the speed of light in water versus air, it'll be slower. And the thing is if you think of light like a vector, right? We'll just draw a little vector here. It's coming down into the water down here, right? Well, if it's coming down to the water and then it hits the water, well, it loses some momentum because its speed has slowed down, not momentum. It loses some velocity, right? So now that its velocity is slowed down, let's just draw a graph, right? We want to do resultant vectors. Up here, the components are what, like this and like this, right? But then it hits the water, so light's down here now. Alright, well, it lost a little bit of its downward momentum, right? Its downward velocity, but it kept its horizontal velocity. So now the angle has changed a little bit. So, you run this through like, you take like a glass of water, you look through. It's because the water goes in, changes speed, and then that changes its angle.
Okay.
And then it leaves the water, it comes out, it's diffracted. Because as it enters the water, it loses some of its velocity. So because when you take two components like this, you go, all right, let's make a resultant vector. So you go like this, and you draw your resultant vector. But if you shave just a little bit off of here, well, suddenly the resultant vector is now a much steeper angle,
Right.
or much
Less of it.
much less of a steep inclination, right?
Right.
So that's why light diffracts refracts when it goes through glass and water, because the mediums change its speed. Yeah.
All right. Cool. 8 minutes.